Okay, so today we're going to be doing 1.5, but I'm also going to start at the warm-up so we can kind of go over that and see how we did with the last lesson. And then also this one requires a graphing calculator, but I have an online calculator we can use, so you can just follow along with that and just go to the website and do it with me. So they'll be a little different from before since you don't have a graphing calculator, a physical one with you, so we can do it online. So for number one, the warm-up, we're going to find the domain range and state whether or not it is a function. So for the domain, remember we have to look the farthest left to the farthest right. That's the x values. And since we have closed dots, we know it's going to be brackets on both ends. Farthest left here is 1. Furthest right is 5. Just fill in the blanks here. The range is the lowest to the highest point. Again, brackets. Lowest point would be, looking across, remember we're doing the y-axis. Lowest point would be 0. It touches the y-axis. The highest point would be 3. It doesn't go any higher than that. Is it a function? Does it pass VLT? I think it does. Oh yeah, functional relation. Function. Domain for the second one. These have both open circles. I'm not sure if that's like that in the notes or not. Because I added them in. Domain is farthest left, farthest right. So if we look at this, open circles, parentheses are going to be on both left and right. First left is -2. Farthest right is 4. Range, lowest to the highest. Now look, this is like a wave. The lowest the wave goes is right around here. So you have to estimate. The highest is here. None of which have open circles. So these are both going to be brackets. The lowest is, I'll say, -2.7. If I can even put it on here. And then the highest is 3. Both brackets. Is it a function? Do vertical line test. I think it always hits 1 point, so it's a function. Okay, so for 1.5, we're going to be doing tables and graphs and kind of reading them and see if we can figure them out. What can a graphing calculator tell you about a function? Although we're going to be doing it online, it still functions the same way. So graphing calculator tell you about a function. So in class we talk about this particular man. I don't know if you've ever seen this guy, but he at one point was known to be the tallest man in the world. I don't know if he still has that kind of, if he like holds the record or not still, but he was pretty darn tall. So we're gonna do a problem based on this guy. As you can see, pretty tall compared to these ladies here. His name was Robert Wadlow. It's in the first example here. Robert Wadlow is the tallest person in medical history whose height has been substantiated. At birth, he was of normal height. And the table below gives his height at various ages A, where h equals f of a. So we're going to talk about this in a little bit. His height is being represented as f of a. So we look here. Age is here. So from 8, 10, up to 22 years old. I'm just going to label this row as A. And then his height was f of a. H was f of a. I'm just going to put f of a because we're going to use this notation, the function notation. As you can see, this is in feet. So he was 6 feet by the time he was 8 years old. And then all the way up to 22 years old, he was almost 9 feet tall. So he was pretty tall. So what is the domain of the function defined by this table? So this goes back to domain and range. When you have a table, you just write out all the numbers for the domain, which is the x values. Now looking at this, you may not know what the x and what the y values are, but like we said before, when you have f of a, that's always your y. Whatever's inside is your x, so this is your x value. So going across the top, 8, 10, 16, 18, 22, those are the values for your domain. 22. And you put them in brackets. The range is obviously the other row. 6.2, 6.6, 7.8, 8.2, 8.8. So now that I labeled this as f of a, hopefully we can figure out what this is. Find f of 16. Again, that's like where your that's the age here. It's saying find 16 and go down, read f of a, which is 7.8. So how do we write this out? It would be f of 16 equals 7.8. Now we've talked about finding this number and then talking about what it represents. So what does it mean? It means at the age of 16, Robert was 7.8 feet tall. So how are we going to write this? At 16 years old, Robert was 7.8 feet tall. That's what that means, this one little equation here. For what value of a does f of a equal 8.8? So now it's actually telling you to go backwards. It's saying, hey, let's look at f of a's row, find 8.8. So f of a is up here, find 8.8. It's over here. And we're going to find the value of a, or the age. So we're going backwards and saying, okay, what is the age? Oh, it's 22. So you could just say 22, like a equals 22. Or you could actually use this here and write it out by putting the a value inside. So you could also say f of 22 gave us 8.8. And that should work, because when you look at 22, it gives you 8.8 in the table. So most of the stuff is something we've done before, except for maybe D, going backwards and reading the table the other direction. Okay, the calculator activity. So a lot of these directions are not going to make sense because we're not going to use them since you don't have a graphing calculator. But we'll read through this and I'll show you how to do it on the website, which I'll link as well. So you can do it on the laptop. Suppose a puddle of water is evaporating and its depth d of t in inches after t days is given by the formula d of t equals 6 minus 1/16 t squared. So we're not going to use this stuff, but I'm going to show you how to put it into Desmos. And so this kind of just takes you through the steps on how to put it on here. So I'm going to show you how to graph this. When we put this in either a graphing calculator or Desmos, which is the calculator online, we have to change this. On the calculator, we're going to do y, because d of t is y, because you have to use y and x's on the calculators. And then the other thing we're going to change is we're not going to use t, we'll use x. So it's 6 minus 1/16 x squared. And I'll show you how to do that on the calculator. So let's go ahead down here. We're going to type this in. So it's desmos.com/calculator. It's y equals. And I just type in 1 and then the minus sign 1. And then use the slash that's next to the shift button. That gives you the division sign. It puts it down the bottom for your denominator. Put 16. And then you have to hit the arrow to make sure you get out of it. And hit X. And then to get something that's squared, you have to hold shift and hit the 6 button. That takes it up. And then hit 2. Oh, I didn't mean to hit 1. The number is 6. There we go. And you can see the graph over here, what it looks like. You can also zoom in with your, I think with your, well, with my mouse, I can scroll in and out. You might be able to do that on the laptop pad as well. So you can kind of see what's going on here, this big arc. Now to bring up a table in here, you have to hit this gear button. And you have to hit this button here. It says convert to table. This will give you some values. And if you want to get more values, which we will want more values than this, you can also see the dots over here. If you want more values, you just click on one of these over here. And if you just hit enter, it will generate more dots on the graph. So I'm going to put a bunch of them on here. Just keep hitting enter. I don't know how to go backwards though. Yeah, so I don't know how to do that. So that one's just undefined. What if I typed one in? Oh, okay. So you can actually put more on and then type in the numbers on the left. So we were going from -3 all the way to 11. And then we're going to answer some questions on the notes. So we can skip most of the stuff here. We're going to go down here. The values in the x column represent which variable in this problem? So these values here, what do they represent? Well, if we go back to what we changed it from, x squared was originally t. So let's write that. They represent t for days. So what do we have happening for this problem? We have a puddle of water, and over time it's evaporating. So we have this, however deep it is at some point, we're measuring the depth of the water, and over so many days it's going down. So obviously the water is evaporating, so the amount of water in the puddle or the hole or whatever is going down. So what is the values of the y sub 1 column represent which variable in this problem? The values in the y sub 1 column represent which variable? So what are the y values? Which is over here. They don't actually say y here. The y values would be, again, going back to this, we changed it from d of t to y here. So it represents d of t. And what are we measuring? Well, we're measuring the time in days, and we're also measuring the depth. And that is in inches, right? So depth, d of t in inches, and after t days. Okay. Do all the ordered pairs in the table realistically model the puddle of water situation? Why or why not? So if we look at the numbers here, if we look at all the numbers on both sides, does it realistically model the situation? Well, there are some that don't make sense, right? If x values mean days, it wouldn't make sense to say -1 days or -2 days. So there is a cutoff at this point. We're probably going to be looking at where it starts at 0 over here, 0, 6. So this one is probably the starting point, because we're going to look at it the very first day. You know, as soon as it's done raining, whatever, we see the puddle, we measure it, it's 6 inches deep. Also, it wouldn't make much sense to continue with the days after it has evaporated completely. And you can see that happening as soon as we go, again, in the negative direction for the y values. So it looks like after 10 days, -0.25 doesn't make sense. That means there's no water at all. You can't measure a negative depth like that. And so that point is over here, right there. 10 -0.25. So really we're only looking at the graph from up here in this arc going down to the point where it evaporates completely. So do they all realistically model? Not all of them, so no. So we'll say can't have negative days. Or how about a negative amount of water? A negative depth. So at some point, only a certain set of points actually makes sense. So going back to this, we're only going to be looking from 0, 6, all the way up to when it changes. So probably the last point, 9.9375. This is the only set of data that matters. Determine the water depth after 6 days. So this is basically saying your t value or your x value. I'm going to write this in d of t notation. So they're saying, what is the depth? So d of, right, this is your t value, days. D of 6 is what? That's what we're going to find. So we look at our table. Where is it 6 days in? Here we go, 6 days. The value of the depth is 3.75. 3.75, and this would be in inches. All right, now we're going to do the reverse. When is the water depth? So now it's telling us the d of t, right? We're going to be finding t. When is it 5.75 inches? Write your answer in d of t notation. So we're going to find d of what day? When does it equal 5.75? This is us writing it in d of t notation. So we're trying to find t. What day is it? So when is it 5.75? Right here. That would be after day 2. So put 2. So d of 2 equals 5.75. So I hope you're able to read the table correctly and kind of understand what each variable means for the x and the y values. So I think we're done with using Desmos, the calculator online. But if you do need to ever use it, that's always like a free option to use to do as a graphing calculator. All right, example 2. Frankfurter rode his bike to Chuck Roast's house to plan a back-to-school picnic. The boys then rode a short distance to the park and then back to Frank's house. The graph on the next page, or on this page in this case, models Frank's trip where T is time in minutes, D is Frank's distance from home in miles. Okay. So we can look at this and we have the time keeps increasing. Frankfurter is riding his bike. So over time, we see his distance from home. So his distance is growing, and then eventually he goes back to home, which is why it comes back down here to the x-axis. So as we see it, it goes up, and then it looks like he stops at some point because his time is increasing, but his distance is not. So it does say he stopped somewhere, right? He went to Chuck Roast's house for a little bit, and then they both rode to the park. So this is like them riding. More time is elapsing, and he's getting further away from his house. Then they stop at the park. So this would be like park. This would be this is Chuck Roast's house. His house. So they go to the park and then back to Frank's house. So it looks like he drives back to his house pretty fast at first, and then at some point he changes and it's not as steep, so it's taking him a little longer to get back home, and eventually gets home after 210 minutes for the whole trip. Okay, express the relationship between Frank's time and distance from home in function notation. So it did say D is Frank's distance, so we're going to use that. We're going to use D and T, so kind of like before, I'm going to say it's D of T. So this would be his distance. Oh my goodness, this thing's not working so well. From home. And T is time. So that's D of T notation, or function notation. State the domain and range of the function. So what's the domain? That's farthest left to farthest right. Looks like it starts at 0 and goes all the way to 210. There's no open circles. 0 to 210. The range is, the lowest point is 0 again. It doesn't go below 0. And the highest point is how many miles? 12. 0 to 12. And then the last one here, I think there's actually some more, isn't there? Yeah. Estimate Frank's distance from home after 60 minutes, and then write it using the function notation. So let's kind of erase some of this stuff here. So after 60 minutes, so we're looking at the time and finding 60 minutes. We're going to go up and read the graph and see what his distance was. So we go up here. At this point, well, how far away was he at this point? Just read across. It looks like it's about halfway between 4 and 8, so that would be 6 miles. So let's write it in function notation. We would say D of, remember, it's up here, T. T is your time. So D of 60 minutes, equals his distance. So D of T equals the distance from home, which would be 6. I hope you can understand where the numbers go. The 60 minutes is your T, so it goes in for T here. Okay, part D. Estimate how much time it took Frank to first reach 12 miles from home. Write your answer using function notation. So same thing as far as the notation. We need D of something equals something. So we're trying to find when he reached 12 miles, so the distance is 12. We're trying to find the T value, right? How much time it took to get there. So we go back here. It looks like he first reached 12 miles. We don't really have to estimate. I feel like it's just perfectly on this line. So we're looking at 12 miles at that point here. Oh, man. It's not letting me make a big dot. And then go all the way down, and it looks like it's about 90 minutes. So to fill this in, what time would it be? D of 90 is when he first reaches 12 miles away from home. All right, as soon as he reaches 12 miles away from home. He's 12 miles away from home for quite a few minutes here, from 90 to 120 minutes, but the first time it happens is at 90 minutes. And the last one here, what is the significance of the first horizontal line segment and the second horizontal line segment, which I think we already kind of went over. The horizontal line segments just tell you that's kind of where they're stopping. The distance doesn't change, right? He stays at 6 miles away from home, but the time is still going across. So what is happening there? Like we said, so the first horizontal distance would be stopped at Chuck's house. And you could even like estimate how long he was there. It's probably like, what would this be, like 45 minutes to 60 minutes? Probably about 15 minutes. And then the second horizontal line, he was there longer with Chuck. Him and Chuck were there at the park. So the second horizontal line was stopping at the park. So that's all the new stuff for this section. There is some questions for the huddle, and I think that's it. Just one or two problems. None of it I don't think you need a calculator for. So you should be able to do this without even having the Desmos calculator online. So go ahead and complete that now, and we'll see you in the next one.